Again, I'd like to thank the organizers for organizing the workshop and giving me this chance to talk. I'd say my talk is a little bit in contrast to the other talks, in that the other talks represent quite, each person represents quite a kind of a group of researchers working on an area. I guess I'm representing a very small kind of group, so one of the aims that I have is hopefully I can win some people over out there who like playing with computers to help us in what we're trying to do. The slides for the lecture are available on the website there, and I've password protected the slides because you don't know the password for tomorrow's slide. Tomorrow's slides are up there as well. It'll be a different password tomorrow. So, yeah. So the problem that I'm going to talk about really for 5 lectures, I'm not going to motivate the problem, I'm just going to state the problem. And it's, if you take your favorite group G, whatever that might be, so it might be a finite group, it might be a Coxeter group, it might be an arithmetic group, it's whatever takes your fancy, then you might want to compute various things. And the things that I'm interested in all relate to, first of all, probably computing a resolution, a sequence of projective ZG modules, or it could be FG modules with F of field, but typically I'll take ZG modules, and you want an exact sequence of such modules. Somehow I want to compute that, and then from that, I want to calculate things like the cohomology of the group. So, having said I won't motivate things, I will motivate slightly. Last week I was at a workshop, and 2 questions that were asked of us at the workshop, both of which I think are within reach. So maybe if people enjoy the lectures, they could have a go at these. Terry Gannon, who was mentioned this morning, was talking about moonshine, and he's interested in the 3rd integral homology of some finite simple groups. The Mathieu group, the monster group is not, is out of range. J4 would be a group he's interested in, but J4 is even something like CO, the first Conway group, I think is probably amenable to what I'm going to talk about, but it's just slightly out of reach, so that's a problem that I'd like methods to solve. I come from topology, so you may also want to calculate things like the Steenrod algebra, the mod P Steenrod algebra. Realistically, on a computer, with the techniques I'm going to talk about, P would have to be 2, otherwise things would get. And various other things. To go back to the workshop from last week, Hecker operators, so Gunther Hard, a number theorist, was there, and he's very much interested in taking a congruent subgroup of some arithmetic group. N is small. And then there are things called Hecker operators. I'm being vague here, whatever they are. And it would be nice to calculate them and to calculate their eigenvalues and so on, because they seem to have they're of number theoretic interest. So again, these kinds of things are motivation. So the typical solution to the general problem is going to clearly depend on the type of group G. And I changed the title of the lectures from Homological Algebra to Cohomology of Groups, because I'm only going to talk about one type of approach, and it's the following. Given my favorite group G, I'm going to try to construct a contractible topological space with a cell structure. I'll explain the details this lecture. And then I will take the cellular chain complex of that space. So that cellular chain complex will be how I'll achieve the resolution I'm looking for. And then the one message I want to get across today and in the subsequent talks is that on a computer, you can have a space, and I'm only interested in contractible spaces, but I don't just want to know that the space is contractible. I want to represent on the computer how it contracts, because it's the homotopy that is used in the calculations. If you look at the typical book on homological algebra, there seems to be an element of choice. You pick something in a kernel, you lift it, and so on. All of the choice can, in principle, be made deterministic if you phrase things in terms of contracting homotopies. So the outline of the lectures, very quickly, and five talks. Today's talk is also different to the other talks in that I'm not going to mention a group. Today I'm only going to talk about topological spaces, and then 4 lectures on groups. So we'd better construct some of these contractible spaces, so that will be the second lecture. The third lecture is not really so mainstream, but I've been interested in it recently. A group can be represented by a classifying space, which is a space with just a single homotopy group. So I'm interested also in what happens if you have a topological space with maybe 2 non-trivial homotopy groups. How would you calculate the homotopy of those things? So that will be the third lecture. More mainstream then is lecture 4, the cohomology rings and Steenrod algebras for finite P groups, finite 2 groups. And in the 5th lecture, I'll go back to constructing classifying spaces and use curvature arguments and so on. So that's the outline. That's a picture of Henry Whitehead. I never met Henry Whitehead. He was the supervisor of my supervisor, but died before I started doing mathematics. But I realized in preparing these slides that actually everything I'm talking about is probably due to Henry Whitehead, so it's amazing how ideas just kind of carry on through academic grandchildren. In particular, Whitehead introduced into topology the concept of a CW complex. He introduced a theory of simple homotopy theory, and he too was interested in spaces with 2 homotopy groups. He represented them using the algebra of cross modules and so on. So the 5 lectures are really describing work of Whitehead on a computer. So let me just begin with the notion of a CW complex, or a CW space. And a CW space then is a topological space. It's a Hausdorff space, something like a torus. And you decompose the space into subsets of different dimensions. So in this torus, there are 4 blobs. There are 4 one-point spaces. The subspaces are open. And then there are several one-dimensional spaces, beginning and ending at a blob, at a vertex. And then I think there are 4 two-dimensional spaces. So each subdivision I'm going to call a cell, and each cell is homeomorphic to a disk of a certain dimension. So it could be 0, 1, or 2 in this example. The space is the union of the cells, and no 2 cells intersect. And then I suppose if this were a topology lecture, I really would worry about the topology, but I don't think we need to get bogged down, because on the computer, it's a combinatorial object. With a little bit of topology, which I'll ignore. So, some CW spaces are nicer than others. So, a CW space on the left is built by taking 0 cells and gluing to 0 cells 1 cells. So I take a 1 cell, an edge, and I glue it to various 0 cells. Then I take a 2 cell, and I glue the 2 cell to the 1 cell. And also in the space on the right, to do the same. The space will be regular if when I glue the boundary, I glue it by a homeomorphism. So I can't take, for example, an edge and put both vertices ends together, because that's not a homeomorphism. I'm interested really in regular spaces, and they can be represented on a computer quite easily. You just have to give the face lattice. So in GAP, this is implemented if you want to play with it. I think in some of the problem sessions, I have some problems on this. To represent such a space on the left, a regular space, you just have a matrix which represents which k-dimensional face lies in the boundary of which k plus one dimensional face, the combinatorics of it. And for efficiency of various algorithms, I list it twice unnecessarily. I list which the co-boundary cells of the particular face. So I list it redundantly because it speeds up various algorithms. So now I want to motivate CW spaces and topology, homology. And rather than jumping into the world of group theory, I thought I would actually jump into a different world of applied topology. So if you Google computational homology, you probably don't find group theorists. You find people in applied topology based at Stanford in Gunnar Carlson's team, or in Krakow in Marian Mozek's team, and so on. And they're very much interested in calculating on big computers very efficiently homology. And I thought I would use that topic to motivate some of the ideas. So a general problem that applied topology is trying to tackle is this problem of big data. You have some enormous data set, S, a sample, from some unknown space, some unknown manifold, and somehow you want to use your finite data to predict what the manifold is that it was sampled from. So let me give a very toy example. I've taken some, I mean, it's so toy that you can see it, and I've taken some data points in the plane. So I'm telling you what the points are. S is a set of points. I'm telling you it's in the plane, but I'm not going to tell you what the manifold is. But you could probably guess something about the manifold. How would you do it though on a computer is the question. We'd want to say, well, probably those points are selected from something like an annulus or something of the homotopy type of a circle. So the idea is that you take your initial sample and somehow, you can do it many ways, you thicken it. And then thicken the thickened version. You repeatedly thicken, and you get a chain of spaces. And then you ask, is there any topological feature which persists somehow in that chain of spaces? And if there is a feature that persists, maybe it's a feature that belongs to the manifold from which the points were sampled. So I take my sample, and then I thicken it a little bit, and I thicken it again and again and again. And then you ask a 5-year-old, is there anything that persists? And the 5-year-old, I guess, I haven't done this, but they'll probably say there's a hole that persists. So how can you capture that on the computer? Well, you can talk of the number of path components, the number of connected components of a topological space. And you can represent your topological space as a cellular complex. Every point in the plane I'll actually represent as a little pixel, and every pixel, for example, I could represent actually as a square with 4 vertices, 4 edges, and a black 2 cell, and then I have lots of pixels. So I naturally have a regular CW complex. And then you can think of some graph theoretic algorithms where to calculate the number of path components. And here are the number of path components for that toy example. The first, our original sample must have been 478 points. And then I thicken, and I'm down to 32 and 9, and then of course eventually I get to 1, which is really what cluster analysis does. But it's not very interesting, because when you take any sample and you thicken enough, you're going to get down to 1 component. So that's not very illuminating, but can be done on the computer. So I want to talk about homology, and the rank of the first homology is called the Betti number, and it tells us how many holes we have in a space. So if I'm looking in the plane, something like that has one-dimensional hole, so it would have Betti number 1. So you could calculate the Betti numbers, and maybe it's a bit more illuminating. Initially, we have 0 Betti numbers. Well, that's because we just have the points. There are no holes. And then you thicken, points coalesce, and you see some of the holes occurring. over there are quite a few little holes, and so on. Little holes and big holes. Here's a little hole. And so on. So it does look there as if we're getting one hole out, but it's still not too convincing, because if you look here, there's a hole that was created and then it disappeared at that stage. So on the other hand, this hole seems to persist, but the data on Betti numbers is not really picking that up. It's just telling me how many holes there are, but I don't know if this one hole here is a new hole or the same hole as that one. But at least they're consistent with the data having been sampled from something of the homotopy type of a circle. As I mentioned then, holes can persist when you thicken. Or a hole could die, because you thicken and it's filled in. And a hole can be born. So there are three things that can happen at each stage, and we'd like to record that. And so let's, for the moment, take this as a definition. I'll give a more mathematical definition soon, but let's take beta n st to be the number of n-dimensional holes in the thickened sample, at stage S that persist all to stage T. Okay? So here's a hole. This space has one hole and it persists. So beta 1, 2, I suppose, is 1 there. So that's the Betti numbers. I'll just repeat it because I'm going to use it a bit. Beta st, it's the number of n-dimensional holes, the n is at the bottom, that persists from stage S to stage T. And what do I mean by a zero-dimensional hole? A zero-dimensional hole, I mean a path component. And a one-dimensional hole is what I've drawn over there. So on a computer, you can calculate, if you have an algorithm, a matrix of the beta STs, the number of holes that persist. And one way to represent such a matrix, which is maybe a bit more insightful, is to write down a barcode. So the matrix there, I'm going to represent that matrix, I hope I get this right now, as follows. Beta ST is going to be, I'm going to represent by horizontal lines, where there are going to be beta ST horizontal lines from column S to column T. So let me look at beta 1, 1, 1. That's 1. So there's one horizontal line from column 1 to column 1. It's a point. Beta first row, second column, there's 1. So there's one horizontal line that goes from stage 1 to stage 2, and then beta 1, 3 is also 1. So I get that. Now, beta 2, 2 is 4. So I've got 4 lines going from column 2 to column 2, but I've got 2 of those lines go from column 2 to column 3. And then the final 4, I've got it right, tells me that I've got another 2 points there. So a picture like that will represent that matrix. In some way. So let's go back to the example. This is the beta 1 barcode of the example. What this tells us is that there were lots of holes that didn't live very long. They were born and died. There was one that lived a little bit here and a few more created there. These are all kind of noise. There's only one line, one hole that persists all the way. So that one hole suggests that there's maybe one hole in the manifold from which the sample was chosen. That's the path component. And just quickly, I mentioned that for path components, the beta 0 barcodes, what they are, they're nothing other than a dendrogram with some information thrown away. Regular cluster analysis is represented using dendrograms, where you record how the various path components coalesce. So the beta 0 barcode is such an object with some information. Okay, so a second example, just very quickly. It's still a toy example, but slightly more convincing, maybe. I've taken a digital image. So a digital image, then, it's a map from the plane. Well, I'm going to do a grace. Oh, no, it's a map from the plane to R3. So every point is assigned a color: red, green, blue. And what I could do, because I want to work grayscale, is I could somehow threshold. I could make a grayscale picture. So I've taken a particular value of t, and I've just recorded all of the points in the plane which are of a threshold less than or equal to t. And then again, I could look at the number of connected components. Naively, you'd hope that the number of connected components is the number of objects in the picture. But if you plot the number of connected components, you see that it really tells you very little. It kind of goes up and down, and you don't gain anything from that graph. But by using the fact that homology, that the number of path components is actually the rank of the zeroth homology, and homology is a functor, you can encode all of this on a computer quite nicely. So if you have an inclusion of spaces, that induces an inclusion of homology, so zero-dimensional homology groups, which I'll talk about in a moment. And then the correct definition, I suppose, of the beta 0 ST, it's the rank of the image of this map of abelian groups. By the rank, I mean the rank of the free path. And then if for that picture you plot the barcode, now I've just simplified things slightly. I've stuck a 19 to represent the fact that there are 19 lines here rather than just one. And there's 13. So if you count the number of long lines, there seem to be 1 and 19. There are just 20 long lines. And I'll put the slides on the web. You can go and you can try to count how many objects there are, and you'll probably find that there are 20. So that's, but very much the fact that the homology as a functor comes into play here. And if you look at the zeroth homology, sorry, the first homology, well, the first homology counts the number of one-dimensional holes. So some of those objects have holes in them. The washers and the nuts and the bolts have no holes. So naively, you would hope that the number, and it works because the example is concocted so that it does work. If you count the number of the persistent lines, they correspond to the number of objects with holes in them. So again, it's a toy example, but it illustrates one body of research that's being pursued at the moment on computing homology. So what is homology? Well, homology is calculated from the chain complex of your cellular space. So given a regular CW space, let's take Cn of x to be the free abelian group with one generator for every n-dimensional cell. And then there's a boundary homomorphism going from the chain group on the n cells to the chain group on the n-1 cells. And it's given by that formula where an n cell goes to a sum of plus or minus 1 times some of the n-1 dimensional cells, just those n-1 dimensional cells that lie in the boundary. Okay, so, and then there's a sign there because we want things to work. We want this equation to hold. We want the boundary of the boundary to be 0. So it is always possible to throw in signs, not uniquely, but you can always solve equations, throw in signs, plus or minus 1, so that you get this equation. And that's the basis of defining homology. So the homology of a space is just the kernel of the boundary map delta n divided by the image of the boundary map delta n plus 1. And you can check that for n equal to 0, that gives you the number of path components. For n equals to 1, it gives you a precise definition of what I mean by a one-dimensional hole. And so let's go back to the example, the toy example. At some point of my thickening, because I took my, I had this filtration, and that's one of the pictures. I need to calculate the homology or something like that. Well, you can count the number of 0 cells, 1 cells, 2 cells. You find that there are 259,000 something 0 cells and even more 1 cells. You take the free abelian group, then all you have to do is calculate the kernel of delta 1 divided by the image of delta 2. So all you have to do is apply the Smith normal form algorithm to delta 2, and you're done, except that these matrices are very large and things like the Smith normal form wouldn't work. The direct application wouldn't work. So this is where Henry Whitehead comes in and his theory of simple homotopy. So if you have a cellular space, Y, it might be that that space is actually obtained from a cellular space X simply by adding in nicely an n-dimensional cell with a boundary 1 n-1 dimensional cell. And if that's the case, we say that Y collapses to X in a simple move. And that's actually an example of a homotopy equivalence. X and Y, in such a case, would be homotopy equivalent. You could write down a homotopy. And I'll record such a collapse just by means of an arrow. So the thing about homology is that homotopy equivalent spaces have the same homology. So in fact, we can do this collapsing to reduce the size of our space and then go to the linear algebra. So there's a picture that I'll make precise in a couple of slides' time. I've taken a tessellation of an interval of size 4 by 4. Cell space, and these blue arrows are supposed to hint at the idea of how I could collapse that space. The homotopy, if I wanted to, I could homotopy it by squeezing it down to a line, then I could push the line into a point. So those arrows, somehow, which I'll make it precise in how, they represent a homotopy. So let me just talk about Bing's house. R.H. Bing was a very well-known topologist who's famous for many things, including his house. And I also find on the Wikipedia, I mean, his name is even more interesting than his house. R.H. Bing, his father wanted to call him Rupert Henry Bing because Bing's father was called Rupert Henry. And R.H. Bing's mother thought that this was a far too British name and wouldn't allow it. So they actually compromised, and his first name was R.H. Simple as that. And then seemingly he applied for a visa to go to some country, and he put down his name as R.H. Bing. The visa application was rejected because he had to put down his first names. So he wrote back R only, H only Bing, and the visa was issued seemingly to Ronley Honley Bing. So anyway, but his house is also interesting. So his house, there's a picture of his house as a cell complex. So the house then is, it has 2 rooms. I don't know if you can see that so well. It has an upstairs room and a downstairs room. The upstairs room is entered through the hallway from underneath the house. You can walk around. And the downstairs room is entered from the top of the house. And that house, and so those are the only entrances. So it's a kind of, it's like a shoebox with a middle floor, with just those 2 hallways going in. And it's not too difficult to see. You can do it in gap, that is actually a contractible space. So he lived, Bing's house is contractible, but it's kind of standard combinatorial topology that it's not possible to represent that house using collapses, as I talked about there. So I mean, it's one approach, but it won't always work. There's some very simple spaces that you can't contract down to a point, but we live with that. So let's come back to the regular torus, which I've represented on the left in a more kind of usual fashion. So let me say what I mean by a discrete vector field. A discrete vector field on a regular CW complex is a collection of arrows, each arrow having a source, an n-1 dimensional cell, and a target, an n-dimensional cell. That's all discrete vector field is. Well, with each cell being involved in at most one arrow. So if you're the source of one arrow, you can't be the source or the target of any other arrow. But not every cell has to be involved in an arrow. So here, there's a few cells that aren't involved in an arrow. This cell, this 2 cell, isn't involved in an arrow. There's no arrow going into the 2 cell. This vertex, 5, there's no arrow going from 5 to anywhere, so 5 isn't involved. So there's some of the cells not involved in an arrow, and I'll call those cells critical. So given a discrete vector field, we'll have the cells are either sources of arrows, targets of arrows, or they're critical. They're not involved in an arrow. And let me put a restriction. I'm only interested in admissible discrete vector fields. So let me take a circle, no interior, with 4 0 cells and 4 1 cells. And let me put some arrows on it. That is an example of an admissible discrete vector field. The following example is not admissible because there's an infinite sequence that we can write down which never stops of arrows. So admissible says that you mustn't have such a situation. And then this is an example of an admissible discrete vector field on the torus. And then there's a handy theorem, which really goes back, well, the idea of the theorem goes back to Henry Whitehead, but it was formalized in work of Robin Foreman in the early 90s, in discrete Morse theory. So the theorem says that if you have a regular CW complex, like we do here, with admissible discrete vector field, then that actually represents a homotopy equivalence to a space Y, where Y is a CW complex, which won't be regular now typically, but it has one set, the cells of Y correspond to just the critical cells of X. So in this example, there's one critical 2 cell, one critical 0 cell, and there are 2 edges not involved in an arrow. There's an edge and there's another edge somewhere. Can't see it. The second edge not involved in an arrow. Oh, down here, this edge isn't involved in an arrow. So there should be a CW space that's homotopy equivalent to the space, and there it is, sure enough, the non-regular one. So on a computer, you can actually represent non-regular spaces by representing regular spaces and throwing in arrows. So let's do this. I started out with this. I'll go with this example of a 2-dimensional CW space, and I said it was too big for me to work through. But it's very easy to design an algorithm which throws in arrows in an admissible way. You could do something along the following lines. There's a space which is contractible. It's homotopy equivalent to a point. Well, I'm trying to end up with a situation. I'm going to look for, the moment, there are no arrows. Let me just make one critical cell here. That cell is critical. Now I'm going to look for cells which have precisely one unlabeled cell in the boundary. But look at this edge. there's only one unlabeled cell in the boundary. So I'm going to label the 0 cell and the 1 cell as source and target of an arrow. Now I'm going to look for cells which have just one unlabeled cell in the boundary. So for example, here would do. This edge has just one unlabeled cell, so I'll stick in an arrow. I can stick in an arrow there maybe, and an arrow there. This edge has only one unlabeled cell in the boundary, so I'll stick in an arrow. And then I come to this edge, if I come to this two-dimensional cell, its boundary consists of 4 1 cells. 3 of those are labeled as targets. So there's one unlabeled one, I'll stick there. And I've ended up very quickly with a discrete vector field involving just one critical cell, which tells me that that space is contractible to a point. So you can apply that algorithm in this case, and what you find then is a much smaller chain complex, a much smaller space. X prime is homotopy equivalent to X. It corresponds to the critical cells. And in fact, there are only 362 0 cells in X prime when you run it on the computer. There are no 2 cells. So you get a much smaller space, and then you can actually write down the chain complex, and you can apply Smith normal form and calculate homology. So let me skip this, because I do want to make some points. Let X be a regular CW space with a discrete vector field. Cn of X is the free abelian group on the cells of X. Let Dn denote the subgroup freely generated by the critical cells. So it's a subgroup. It's not too hard to take these pictures, this topology, and translate it into algebra, and to show that there is a map from, this should be a Dn minus 1, apologies. There is a map from Dn to Dn minus 1 such that the inclusion here admits a kind of a projection the other way, satisfying these two properties. That the square of this is 0 and the square of the delta n is 0. So basically, we're saying that on the computer, you can take this chain complex and you can build a smaller chain complex. But you would also record on the computer these contracting homotopies. Okay, so, I mean, the only message I want to get across with this slide is that when you do this reduction, you don't just, once you reduce, you don't throw away the arrows. You store the arrows on the computer, because that's what makes everything constructive. So that's the idea of that slide. And now I can come to a group. Okay, I have a few minutes to talk about the group. So how does this apply to group theory? Well, the homology of a discrete group G is defined as, or the cohomology is defined by taking any free resolution or any projective resolution. So what I'm going to do is I'm going to construct a contractible space on which the group G acts. So G moves the cells around. So now my chain groups, my CNX, they're not just abelian groups, they're modules. So I actually have a complex of ZG modules. The space is contractible, means that the homology is the same as the homology of a point. It's 0, so it's a resolution. So whenever you get such a space, you're in business. So let's try it with a group. So if you take the group G generated by 2 elements A and B with one relation, BAB is equal to A. And in this example, if you take your space X to be the plane, then it's possible to get G to act on the plane by the following. So you let, what does A do? What does B do? B just shifts. B is translation 1 unit up in the Y direction. And what does A do? A shifts 1 unit in the X direction and flips. It's a shift and a flip. And you can check, I won't do it because I'll probably get it wrong, that if you do B, maybe I will try. If you do B, I'm up. So if I start here and I do B, and then I do A, which is I come over here and I flip. Depends which way I'm if I do B, and then I do A. There's an inverse missing, isn't there? There should be a B inverse. There's an inverse missing. I think there's an inverse, I mean, there. B inverse, it's the same as doing A. So I'll correct that slide. Yep, there's an inverse missing. If you take the quotient space, it's the Klein bottle, and then you take the homology of the space, and that gives you a functor, contravariant functor, from groups to abelian groups. And again, this is the message you want to get across in this lecture, is the contracting homotopy is very important. So all of these arrows, if your space is contractible, so for example, this, I think I had a picture of it. The plane is contractible. Here's an admissible discrete vector field. You can extend that out infinitely. The plane contracts this way, and then you squeeze the line down. You've got all of those arrows. You can write down an explicit formula for the arrows. You don't have to record them. Well, those arrows, algebraically, can be recorded as what I call a contracting homotopy. The arrows go from dimension n-1 to dimension n. You can record them as homomorphisms from, well, in this case, Cn-1 to Cnx, and they satisfy this relation, which is algebraically a chain homotopy. So, to finish off today, I think I'll go back to the next slide. I'll go back to the piece of gap that I skipped. Let me say a bit more about my example. Okay, this was the example where I took the file of nuts and bolts. So on the exercises, I think there are some problems like this. You may want to take a picture and you want to read it as a pure cubical complex. So a CW complex represented in a cubical fashion. So read image as pure cubical complex does that. If it's a color picture, you have to first of all threshold. So I think the RGB values each go from 0 to 255. So you're taking the sum. So you choose some number between 0 and about 750. The threshold at that point, and then you get a black-white or blue-white space. And that's a pure cubical complex represented as an array of zeros and ones. The next command converts that into the format that I mentioned on one of the first slides of a regular CW complex. It gives you the face lattice. And then the next command gives you the very large chain complex, which was too large to apply Smith's normal form to. So what you can do alternatively is take your original cubical complex, and at the level of arrays of zeros and ones, you can do a certain amount of homotopy collapsing, which is what contracted complex does, give you a smaller pure cubical complex. Then convert that to a regular CW complex. And then further at the level of arrows, contract the regular CW complex. And now take the chain complex of this, which will be fairly small. And I do have 5 minutes. So the second example, which I will stop on. Well, let me just, I should say that first of all. I've said it, but I should mention the slide. In classical homological algebra, we often want to take something in a kernel, say it's in the kernel, therefore it comes from something in the image, and we want to lift. On the computer, you can do that with a contracting homotopy. just by setting the lift equal to the contracting homotopy applied to X. So that piece of algebra makes things constructive. And then the final example, which is maybe of interest to group theorists more than pictures of nuts and bolts. Could you ever hope to get a theorem out using discrete vector fields, a theorem in group theory? Well, I don't know, but here's an attempt. So suppose you take your group G, your finite group, and you take the non-trivial elementary abelian, P elementary abelian, subgroups of G. So you get all of these subgroups. They form a poset by inclusion, the non-trivial ones. They form a poset. And that poset gives rise to a simplicial complex. That simplicial complex is the order complex of the poset, and that's known as the Quillen complex for your group. And so here's a proposition which I found from Santini's PhD thesis from about 2000 in Lausanne. Very nice thesis, but I mean, it was a good source of me to get some group theory examples. And he proved that up to homotopy, that should be homotopy equivalent, that's up to homotopy, that means. Up to homotopy, the Quillen complex, the simplicial complex for the symmetric group S7 is actually just a wedge of two spheres. So how could you do that in GAP? You can create the simplicial complex. It's not too big, actually. There are only 11,000 simplices in it. You convert it to a regular CW complex. And then you say, well, my regular CW complex has 11,000 cells. What can I say about it? So you can ask, what are the critical cells? So let C be the set of critical cells. And you can ask, how many critical cells are there of dimension 0? There's just one of them. So you've got one vertex. How many critical cells are there of degree 1? There are none. And how many critical cells are there of dimension 2? There are 160. The only way that you can build a CW complex out of 160 two-dimensional cells with one zero-dimensional cell is to take a wedge of 160 spheres. And then the way that the group G acts on the Quillen complex is important in group cohomology up to homotopy of the Quillen complex. So things like that do happen in group theoretic. I will stop.